Yes, sir.
Okay. Okay. So see, so yeah. So whatever we discussed, yeah, you think about it. Okay, you will. Yeah. If you have any problem, I can discuss it again. But yeah, I think we have discussed it quite a long time. Yeah. Uh, and then we have this is with this same exercise there is something is called Dubdinkin lemma. Or, this is quite famous result. Okay, so it's called Dubdinkin lemma, and so yeah, we just state the lemma. We don't go to the limit, go to the put. So it's like let uh, then uh, so so so, this says that suppose you have a random variable, this x is a random variable, and any sigma x measurable random variable, you can write it in sigma x. If y is a sigma x measurable random variable, then you can write y as f of x for some Borel function R2. Okay, so 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 in a sense that if you have random variable and sigma x, so you can I mean you have a random variable x, then you can always write sigma x, right? You can I mean sigma algebra generated by a random variable, and then any random variable which is sigma x measurable can be written as f of x, where f is a Borel function. So saying that any f of x measurable random variable, you can write it as a form of f of x. Is it clear? So in a sense that we can write another if and only if condition. I mean we can so see this. Let's write another something. Uh, uh, so let's write. I mean this form. I mean another statement or something. Another type of statement. Let me write. So 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 if so suppose if x and y, these both are random variables, omega to r, or just or you just write it as r given functions, or you just write it as this. And so y, uh, I mean, you see, when we define the random variable, what is a random variable? It is nothing but the exercise such that. So in a sense, this statement, it takes care of that previous exercise and these two thinking lemma. So this is a special case of the thing. So you have a two given functions, and y is sigma x measurable if and only if there exist a Borel function such that y equal to f of x. Right? Uh, that is what we have also seen here, right? That I mean, f compose x is a map from capital omega to r, right? F compose x is a map from capital omega to r. So, so that is what we are stating here. Y is nothing but the f compose x. That is what we are stating here. That I mean, here the previous exercise told that f is a Borel function, x is a random variable, f compose x is sigma x random, sigma x measurable. Okay, sigma x measurable. And Duplinkin lemma says that for any sigma x measurable random variable, you can write that random variable in the form of f of x. Okay. And this, the last statement gives an if and only both way. I mean, that is what this last statement combine that exercise and Duplinkin lemma that if you have two given functions, or you can write f measurable functions, x, y are f measurable because random variable is a f measurable function. So if two given functions, then One, why is sigma x measurable if f is a Borel function? So if and only if means there are two statements, right? So then why is sigma x measurable? Just understand. I mean, if you have a, I mean, most of the cases, this exercise is good enough. I mean, that is very much thing which you will use in many cases. Say, f is a Borel function, x is a random variable, f compose x is sigma x. This exercise is good enough. Those are just to know that you can have a both way thing, but most of the cases, I think this exercise is good enough that you just need a, you just have to know that sigma x, f of x is sigma x. That's good enough. Okay, so yeah, these things we have done now. Now I go to define some. So something. 1 hour, right? No, no, you remember what is the probability measure we have defined? Yeah, I think we have defined the probability measure, right? Yeah, yeah. So probability measure is nothing. It's also so random variable is a real valued function from capital omega to R, and probability measure is also a real valued function from sigma algebra to the 0, 1 interval, 0, 1 closed interval, which satisfies these two properties. One is probability of capital omega is equal to 1, and another is that if you have a pairwise disjoint sets, then they are pairwise disjoint sets, then their probability of union AI is equal to summation probability of AI. These two are definition of probability means. Correct. Uh, and these two are definitions of probability. And and what are we? Just a moment. Just a moment. Yeah. So what is saying is that if this definition is saying that every random variable gives rise to a probability measure. You see, so for any random variable corresponding to a random variable, you can define a probability measure. Or it's some sort of existential this thing, some sort of existential. So I'm audible, right?
Yes, sir.
Yeah. So this is some sort of existential thing that when you will have a or I mean the existence of a probability measure. So what does it say? That every random variable guarantees you there exists a probability measure over R, right? And yeah, so this is a notation. This is a this is something notation. This probability of PXP, you define it as probability of X belongs to B. And I mean, for any Borel set in these, and we I mean, and we have just uh, for any random variable, uh, X belongs to B means so X belongs to B means what? I mean, we have again we have to see that this. I mean, you have X belongs to B or X inverse A belongs to F. I mean, these are for random variable F measurable, these both are equivalent, right? I mean, you can write it X belongs to A or X belongs to B or X inverse A belongs to the sigma algebra. So, yeah. So in a sense that, yeah, I mean, similar, I mean, in a sense that you can have this, so, or same thing, the notation. In a sense that every, I mean, a random variable, every random variable induces a probability measure on R. So in a sense that you can say that every random variable induces a probability measure, and this is the definition that PXB is equal to this or this or this is the definition. And yeah, and another thing is another thing is PX. Okay, is called the distribution distribution of distribution of distribution of random. Um, yeah, I mean, so I mean, distribution function. So in a sense that we write it right. And this you have already known, but it is in this way the definition distribution function. So fx. Right? So this fx is a map from R to 0, 1. Right? And small x is defined as you people have already done in the probability course what is a distribution function. But here we are defining it with the probability measure as probability. This is the outlook of these things. So you see the probability. So it's a map from real R to 0, 1. I mean, you see. So the small x is an element of R, and this is, I mean, what is this x less than equal to c? So it is like probability of this set omega such that x omega less than equal to x, right? For x belongs to R. So probability of omega such that x omega less than equal to x such that x is in R. I mean, this x less than, this is a shorthand, this is abbreviation. This means nothing, that probability of omega such that x omega, I mean, the set consists of those small omega such that x omega less than equal to x, small x, for x belongs to R, real value. So distribution function is a map from capital R to 0, 1. I mean, this is pretty fine, right? Because it's a probability measure is a map from f to 0, 1. So the range is always 0, 1 because fx is defined as probability of x less than equal to x, small x, capital X. Yeah. So yeah, we'll continue to do these things. And then there is some this thing of the distribution function, some we have some this thing of distribution function, some properties of distribution functions, and we'll discuss about it. Okay. Okay. So yes, we stop it here today. See you again on Thursday. Thank you.
Thank you, sir.